Hello, hello, hello. Am I audible, guys? Just give me a yes in the chat if I'm audible. All right. So, hi everyone. Welcome to the PCD of today's CF round 1020, which was Division 3. And today we'll discuss the problems from A to F. And before we get started, I will tell you about the TLE's all new CP sheet. So, if you don't know, this sheet contains 31 handpicked problems from all the ratings from 800 up to 1900. And all the problems are handpicked in such a way that each teaches unique idea. Also, you can connect your CF account to this sheet, so it will fetch your submissions automatically. And there's also a leaderboard where you can compete with the friends and peers about who solves more problems. And yeah, there's also a discuss section here where you can make comments, and there's also a solution video. Like every week they will be uploaded, and till now we have uploaded 2000, so you can watch them. Anyways, so let's start with the first problem of today's PCD. So this was today's first problem. Dr. TC, in order to test his patient's intelligence, Dr. TC created the following test. First, he creates binary string S having n characters. Then he creates n binary strings A1, A2 up to AN. It is known that AI is created by first copying S, then flipping the ith character. After creating all the n strings, he arranges them into a grid where the ith row is AI. For example, if S is 101, then A will be 001, 111, and 100, and if S is 000, then A will be this. The patient needs to count the number of ones written on the board in less than a second. Can you pass the test? Okay, so we have a problem which is we have been given a binary string. Okay, so let's say it is something like 01001. Okay, and then what you do with this binary string, you just create a matrix. And how do you do that? Simply what you do is you just write this binary string 5 times, like n number of times, right? And all of the elements on this diagonal, just flip them, right? So these elements will be flipped. So like here is 0, so it is 1, 0, 1, 1, and 0. So this is what the final matrix looks like. And see, if you are confused, the problem doesn't say that we are flipping this diagonal, but it says that we are flipping the ith character in the SIth string. So basically, in the S1 string, this is S1 string, right? So in the first character will be flipped, right? Sorry. In the S2 string, this will be flipped. In S3 string, only this will be flipped, and so on. So as you can see that these characters are flipped, right? And what you need to tell them is the number of ones on the board, right? The number of ones on the board, you need to tell them. So how do we count this? Let us count this row wise. Like, okay, first of all, even if you just make this matrix, like let's say you just construct this matrix and just count the number of ones, then also it will pass. Like that is O of n square solution, right? That is O of n square. But still it will pass. Like they have given the limit of n very small. So it is up to 10 only. So t into 10 square will definitely pass. So even if you do that, it is pretty easy. But I'll tell you the approach which is O of n. Even O of n is possible here. So I'll tell you O of n. So what you can do is, you want to count the number of ones, right? You need to count the number of ones. So what you will do is, you will just count the number of ones in each row. Like suppose the first row is here. So what are the number of ones? Then in second row, what are the number of ones? And so on, right? So let's see there were no flips. Like let's assume there were no flips. Then of course the number of ones would be just how many ever number of ones are there in the string. Like in my string I had these two ones, right? This one and this one. So the number of ones in each row would have been 2, right? I could have just said that each row had two ones. Like this row had two ones, this row had two ones, this one has two ones, this one has two ones, this one has two ones. So finally the entire matrix would have 10 ones, right? But now it is not the case, because on the diagonal we are changing, right? We are flipping all the ones to zeros and all the zeros to ones. So essentially, like in the first row, this first character is flipped, right? This 0 is there in the first row and it is flipped to 1. Then in second row, this 1 is there and it is flipped to 0. Then in third row, this 0 is flipped to 1. So I can say that uh, exactly once, like in my initial string, whatever characters are there, they are all flipped exactly once. Like this first character has been flipped in just the first row, then this character has been flipped in second row, and so on. So guys, can you notice that? Like that's what my point is, that every character will be flipped exactly once, right? So yeah, that is the observation here. So what you can just do, like let's say you flip a 0 to a 1, right? Like if you flip this 0 to a 1, then the number of 1 increases by 1. So here we had counted 0, right? Like when we are saying that there are two ones, two ones, two ones, two ones, and two ones, we are not counting this one because it is flipped. So we have to count this one extra. So this is plus 1. Then when we say that there is a 2 here, like two ones here, then we are also counting this thing right here, because it was initially 1 in our string. So we have to actually subtract minus 1 from it, right? So how many times should I add? And like this is plus 1 because initially it was 0, and now we have flipped it to make it 1. And this is minus 1 because initially it was 1, and now we flipped it to make it 0. So essentially what we can just do is take this 2 2 2 2 2 and like 10, and what you will do is minus count of 1 plus count of 0 in your string. Like in your string, the number of count of 1 and the count of 0 you will do, like minus c1 plus c0. Why you will do that? Because uh, all the zeros that you make to 1, they will increase your count by 1, and all the ones that you convert to 0, they will decrease your count by 1. So essentially the total number of ones in your grid will be changed by this amount, minus c1 plus c0. Okay, so guys, is it clear? If someone like has a doubt, then they can ask me. Like what I am trying to say is that since like we have, let's say we have 0 1 0 1, so we made the matrix 0 1 0 1, we wrote 4 times, and 0 1 0 1, and you just count the number of ones in this, so that is 2 into 4, which is equal to 8, right? And then you flip these diagonal, then you flip these elements, and if you can notice that this is the first element, this is second element, this is third element, this is fourth element. So essentially you are flipping every element exactly once. So all the zeros that you convert to 1, you will add 1. So you will just do plus count of 0, and all the ones that you convert to 0, you will subtract 1. So you will do minus count of 1. So that's the thing. Okay, all right, so I think it is clear to all, so I'll show the code now. Okay, wait. Yeah, so this is the code: int n, c in n, string s, c in s. All right, and c0 is the count of zeros in my string, right? This is the count function. and the count of 1 is n minus c0, count of 0. And your final answer would be the initial count, which is count of ones into number of rows, right? And you just add c0 and minus c1 and new line. Okay. All right. So I think the code should be clear, and I'll move on to the next one. Problem B says Saint Chroma. Given a permutation of length n that contains every integer from 0 to n minus 1 and a strip of n cells, Saint Chroma will paint the ith cell of this strip in the color max of p1 to pi. For example, suppose p is 1032. Then Saint Chroma will paint the cells of the strip in the following way: 0, 2, 2, 4. You have been given two integers n and x. Because Saint chromas love the color x, construct a permutation p such that the number of cells in the strip that are painted color x is maximized. Okay, so your problem says that you have a permutation, right? So you have a permutation which is like from 0, 1 to up to n minus 1. It is a rearrangement of these numbers, right? Okay, and then what you do, like you take this permutation. Okay, so let's say you have p0, p1, p2 up to p of n minus 1. Actually, in the problem they have said p1 up to pn, so I'll say that. So p1, p2, pn minus 1 up to pn. So this is what your permutation is, and what you will do is you will create a new array where a of I is the prefix max of p, prefix max of pi, like basically max of the set p1 up to pi, like that is ai. That is how you define ai, right? So they are telling you to construct a permutation of length n, right, such that the number of times x appears is maximized. Okay, that's the problem, that you have to construct a permutation of length n such that in the final array A, the number of times x appears is maximized, right? So, and here the limit of n is up to 2e5, so you have to do it in O of n, obviously. And so yeah, so let's think about this. How will we solve this? So first of all, let's see that what will happen if I construct an array A. Like I'll show this how to construct this array. So like 1032. If we have p as 1032, then what is my array A? My array A will be what? Like A1 will be just the max of the first number. So what is the max of this set 1? It is simply 0, because 0 is not present in the set. Then 1 comma 0. 1 comma 0 max is 2, because 2 is not present in 1 comma 0 and other elements are present. Then 103, the max is still 2, and 1032, the max is basically 4, right? So this is your final array A. And basically what you want to do is you want to ensure that x appears the maximum number of times. You have n and x, so you want to create a permutation of length n so that x appears the maximum number of times in the array A, right? So like how do we do that? Now actually, first of all, let me say my claim. Okay, so what is x? X is basically element of A, right? X is the number of occurrences, like x is an element of A. Like we want to maximize the number of times x appears in A. So basically x is an element in A, right? And what does it mean? Like basically x is a max. X is a max of some numbers, p1, p2, p3 up to pi, right? Like what I am saying is, if my ai, if some ai is x. Like in my new array A, if the ith element is x, then that means that it must have been the max of p1, p2, p3 up to pi. Right. But guys, as you know, that max of some elements, like max of, let's say, uh, if I have k elements b1, b2, b3 up to bk, if I have k elements, then what can their max be at max? Like at max, their max can only be k. Like it cannot be more than k, right? The max of k numbers can be at most k. Like that is in the case where all of the numbers from 0 to k minus 1 appear, like 0, 1, 2, 3 up to k minus 1. If all of them appear in this set, then its max will be k. And if any one of them doesn't appear, if any one of these numbers does not appear, then that will be the max. Like the smallest number which doesn't appear, that is the max, right? So it can be at most k, right? So let's say you have n equals to 5 and x equals to 3 as your input, right? So you basically want your max to be 3 at some index. So like let's say you have this array A. See, length of P is 5, so length of A is also 5. So this is my array A, let's say. So what I am saying is that here 3 cannot be there. Like there, it is impossible to put 3 here. Why? Because 3 cannot be the max of just one element. It will be either 0 or 1. Like the max of one element is less than equal to 1. So it cannot be 3. Right? So 3 cannot be here, 3 cannot be here. But actually 3 can be here as 3 can be here. Like it is possible that 3 can be here. Because it is the max of 3 elements. So how do we put 3 here? Like how do we ensure that 3 comes here? We have to ensure that, see, what is A3? Like this is A1, this is A2, this is A3, right? So this A3 is the max of P1, uh, P2 and P3. So if I want A3 to be 3, then of course I should have that 0, 1 and 2. Like these three numbers should be 0, 1 and 2. That is necessary. Like P1 has to, like I'm not saying that P1 has to be 0, P2 has to be 1, P3 has to be 2. Like any order can be there, but these three numbers have to be 0, 1 and 2 in any order. Okay, so let's just set that P1 is 0, P2 is 1 and P3 is 2. So let's just make the permutation. Like this is my P. Okay, let's say I'm creating P. And in array A, in these two indices, there is not 3. And in this index there is 3. And how there is 3? Because there is 0, 1 and 2 here. Right. Now, here also we want 3. Like we want to maximize the number of 3's, right? So we would prefer that here also we have a 3. So what do I do here? Like what do I insert here? So let's say I put a 4 here. Then the max of these first 4 numbers will also be equal to 3. Right? So that works out fine. And now fifth number I have to put 3, right? Like I have to make this a permutation. So I am forced to put 3 here as my last number. So here the max cannot be 3. Right? So at 2 indices my max has become 3. And actually as you can see that in these 2 indices max could not have been 3, because these are the max of just 2 numbers. Like this is max of 2 numbers, this is max of one number. So they could not have been 3. And also this last number also could not have been 3, because it is the max of all the numbers. So the max of all the numbers from 0, 1, 2 up to n minus 1, it is definitely n. So it cannot be 3. Right? So yeah, that's what I'm doing. That so simply, what's my construction? My construction basically is that I just put all the elements less than 3 first, like 0, 1 and 2. So their max is 3. Now if I put a 3, then my max will increase, but I don't want that. So I'll skip a 3 and then I'll insert like higher numbers. So let's say I have n equals to 7 and x equals to 3. Let's take this example. Then what will I do in that case? I will construct, let's say this is my p. Then I will put 0, 1 and 2 here. Then I will not put 3 here. Right? So I'll put 4, 5 and 6. And at the last point I am forced to put 3. So if you see that the max of this array, what does it become? It becomes like not 3, not 3, and here we have 3, here we have 3, here we have 3, here we have 3, and here we have, of course, we have 7. Like last element will definitely be 7 or like n, right? So that's what I have constructed. So finally my construction is just uh, 0 up to x minus 1. Then we have x plus 1 up to n minus 2, and then we have x, sorry, n minus 1, and then we have x. This is my construction. Okay, so I hope it is clear why it is optimal and like how am I constructed it. And actually here there is one more edge case that see, here I am putting x, right? Like 0 to x minus 1, then x plus 1 up to n minus 1, and then x. So I am putting x in my array, but my elements must be between 0 to n minus 1, right? So my x, I am assuming that it is between 0 to n minus 1, but it is given that x can be uh, like 0 less than equal to x less than equal to n. So x can be also n, like x can be n as well, right? So basically what they are saying that they want this max to be equal to n, but that can happen only in one index. On the last index only that can happen, because that is only the max of n numbers. All the previous indices are the max of less than n numbers. So the only way I can put n is on the last. Like in my A array, in my A array, n can only possibly occur on the last, and it will always occur on the last. Whatever we make the permutation, it doesn't matter. Like let's say we just make the permutation as 0, 1, 2, 3 up to n minus 1. Then my last index would be n, and no other would be n. But that is the maximum. Like I can only have n at max one number of times. So that is the answer. So if x equals to n, then I just print this permutation 0, 1, 2, 3 up to n minus 1. And if x is not equal to n, then I print 0 to x minus 1 first, then I skip x and print all of the other numbers, and then I print x. Alright. So yeah, I hope it is clear. If someone has a doubt, then please let me know. Like summarizing, since we want that 3 becomes like 3 comes maximum number of times. So of course in first and second index we cannot put 3 because it is the max of 1 and 2 numbers. But from third index onwards we can put 3. And we have ensured that there is 3 everywhere. Except for the last index, it is not 3 because it cannot be 3. So this is the maximum. Okay. So guys, I hope it is clear. Just give me a yes in the chat if it is clear. And if it is not clear, then let me know the doubt and I'll answer it. I think it should be clear, so I'll show the code. So we have ln nx seen nx. If x is equal to n, this is my edge case. So I'll just print 0 to n minus 1. So for int I equals to 0, I less than I plus plus, I see out I and space. So see out I and see out a new line. So this is what I print if x is equal to n. And otherwise, I print like for int I equal to 0, I less than x, I plus plus. I answer push back I. Then from x plus 1 to n or to n minus 1, I do answer push back I. And then in the end, I push back x. And then I just print the vector which I have created and see out n line. Okay. And actually here I should not have used x variable because x is already used up here. But C++ just assumes that I'm talking about this x when I try to print x. Okay, so but anyways, so I think it should be clear. So I'll move on to problem number C. Cherry bomb. Two integer arrays a and b of size n are complementary if there exists an integer x such that ai plus bi equals to x over all I from 1 to n. For example, the arrays 214 and 341 are complementary since ai plus bi is 5. However, the arrays 13 and 21 they are not complementary because 1 plus 2 is 3 but 3 plus 1 is 4, so it is not equal. Cow the nerd thinks everybody is interested in math, so he gave Cherry Bomb two integer arrays a and b. It is known that a and b both contain n non-negative integers not greater than k. So all the integers are between 0 to k. Unfortunately, Cherry Bomb has lost some elements in b. The lost elements in b are denoted with -1. Help Cherry Bomb count the number of possible arrays b such that a and b are complementary and all the lost elements are replaced with non-negative integers no more than k. Okay, so basically what they are saying is that we have, so for two arrays a and b of same length, like array a of length n and array b of length n, we call them complementary if ai plus bi is equal to x, like it is constant. ai plus bi is some constant value over all the values of I, right? So that's what complementary means. And what they have given us are basically, they have given us an array A. The whole array A they have given us. And they have also given us an array B. But in the array B, some elements are missing. Some elements are missing. Like in array A, all the elements are there. But in B, some are missing. And what I have to tell them is that how many possible number of arrays are there, like arrays B are there, such that A and B are complementary, right? So complementary means that their sum should be some constant value x. So this sum should be x, this sum should be x, and so on. Now, how do we like solve this? Actually, see, they have given us that in the array A, all the elements are present, right? So we don't need to worry about that. Okay, so let's take a sample test case, alright? Let's say we have 132 and -1 -1 1. We have A as 132 and B as -1 -1 and 1. So um, what I need is that these two are complementary. So as you can see that in the array A, all the elements are known, and the array B, only one element is like known, and baki two are unknown. The other two are unknown. So actually, I can use this element. So like I can find out the value of x now, because I want that sum of all of the indices should be same. So since the sum of these two is same, so 2 plus 1, which is equal to 3. So I want that sum of these two also should be 3. So -1, like this 1 and this number, this hidden number should also be 3. So I need a 2 here, and this 3 and this -1. So here I need 0 to make it 3. So basically, my B array will be 201, right? And obviously, there is only one possible array because there is only one value of x. 2 1. See, on this 2 1, through this 2 and 1, I know that the sum is 3. And since I know the value of ai plus bi, I know the value of ai plus bi is 3. And also I know that the value of ai is what? Like, I know the value of ai for all the integers. So of course I know bi also. I know the bi value for all the integers, that is equal to 3 minus ai. Right. But I also have to verify that this value that I have found out, it also lies in 0 to k range. So this value also should lie in 0 to k range. So while we are iterating through the arrays, we also have to ensure that they lie in the 0 to k range. So here, as you can see, that the k is 10. Here the k is 10, and this 2 and 0 lie in the range of 0 to 10. So that's why I can say that this array B is possible, 201, and therefore the answer is 1. But let's say it was going out of range. Like if any of these elements was going out of range, then I would say that the answer is 0. Right. So that is the case when I already know one element of B. Like when I know one element of B, then my answer is either 0 or 1. 0 or 1. It is 0 if my hidden elements are not in the range, not in the range of 0 to k. If any of the elements are not in range 0 to k, then I'll print 0. Like there are no errors possible. And if all the elements are in the range of 0 comma k, then I'll print 1. Right. So so what I am saying is that okay, that case is handled when at least one element is known. Like when at least one element of B, at least one element of B is known, that I have handled, right? So what is remaining? Now what is remaining is all of the elements of B are unknown. Like B is basically minus 1, minus 1, minus 1, minus 1. All the elements are minus 1. If all are minus 1, then what can we do? Right. So guys, we want to count the number of arrays B, right? The number of different arrays B. So isn't the same as counting the number of values of X? Like if my AI plus BI is equal to some constant value X, right? It is equal to some constant value X. Then if I just count the number of values of X, the number of different possible value of X for which all of the BI come in the range from 0 to K. If I count all of those values of X, then isn't that the same as counting the number of arrays of B? Counting the number of arrays B, that is the same. Because if I fix my X, like if I choose a certain X, then my array B is also fixed. Like corresponding to an X, there is only one B. And of course it is distinct because my BI is X minus AI. So if I choose X to be different, then my BI would be different. So all I have to do now is just count the number of X's which satisfy that all of the BI elements should be in the range of 0 comma k. Right. This is the case when all of the elements of B are unknown. Correct. So let's take this case for example. Here we have all of the elements unknown. So 1, 3, 2, 5, 4. And so A is 1, 3, 2, 5, 4. And B is minus 1, minus 1, minus 1, minus 1, and minus 1. And we want the range 0 comma 10. Right. So my all of BI, like all of my BIs should be in the range of 0 comma 10. So I can say greater than equal to 0, less than equal to 10. Or in the general case, let's say I want it to be less than equal to k. So what is my BI? Like if I know my X, If I know an x, then bi is what? Then bi is just ai minus x. Ai minus x, right? I can write bi as my ai minus x. Correct. So I want this thing to be true for all of the ai. And since I know the value of ai, I can simply isolate that. Sorry, my bad. X minus ai. Alright. ai plus bi was equals to x, right? This was equal to x. So my bi is equal to x minus ai. Right? Not ai minus x. 1 minute. We have like bi is x minus ai. My bad. So we have x minus ai, and we want this value to be in the range of 0 comma k. So ai less than equal to x less than equal to ai plus k. So basically my value of x should lie in this range for all ai. Like for all the ai, my value of x should lie between this range, right? So for example, in this case, if I see, like I have array a as 1 3 2 5 4 and my k is equal to 10. So what I want first thing is that, like, if ai is 1, so I want x to be between 1 and 1 plus 10, so 11. I want x to be between 1 and 11. Also, I want x to be between 3 and 13. Also, I want x to be between 2 and 12. Also, I want x to be between 5 and 15. Also, I want x to be between 4 and 14. So, these 5 conditions, I want to satisfy them, all of them at once. So, what does that mean? That basically I can just take the maximum on the LHS. Like here, I want x to be greater than 1, x to be greater than 3, x to be greater than 2, x to be greater than 5, x to be greater than 4. So, essentially, if I say that x to be greater than 5, so doesn't that just include all of these other ones also, right? And also I need x to be less than equal to basically 11, 12, 13, 14 and 15. So I can say that x should be less than equal to 11, right? So this is my range of x. This is my x range, and what I can simply do is I can take the number of elements, which is 7. In this range, the number of elements of x is 7. 5 to 11, there are 7 elements, and therefore the answer is 7. Like, since there are 7 different values of x, I can have 7 different b arrays. So yeah, that is the final solution, that you just write out the different conditions on x and just take their intersection. And or essentially what I am saying is, just take the maximum in these two, like in maximum in these 5 and the minimum in these, and that is your final range for x. And if somehow, let's say your array a was 1 2 and 3, and your array, or okay, let's say your array a was 1 5 and 10, right? And k was 3, let's say, and your array b was of course -1 -1 -1. Wait, k cannot be 3, because the elements of array a also has to be between 0 to k. So wait, like my point was that, what if the intersection of these intervals turns out to be empty? Like, it is, I thought that is also possible, that the intersection of these intervals is nothing. So in that case, you would print 0. right? But I think that is not possible because the elements of A are also bound to be between 0 to k. Like since the elements of A are also bound to be between 0 to k, so therefore the intersection of these intervals will not be null. Okay, so you just take the maximum of these and the minimum of these, and then just print the answer. So yeah, there are two cases that if any one element of B is not equal to -1, then we can determine the value of x. And if any, like all of the elements of B are -1, then we have to just count the number of different values of x for which it is for which the condition is satisfied that my BI has to be between 0 to k. All right. So yeah, I hope it is clear. Like, is the logic clear? If it like, just ask me any doubts if you have. Everyone, do you have any doubt? Clear. Okay, so I'll show the code. So yeah, I have seen LLNK, seen NK, input the array A and input the array B. So it just creates an array A and inputs it, and creates an array B and inputs it. This is the macro, and this is my rough work which I did during the contest. So yeah, so I just count the number of -1s in my array B. If it is not equal to n, right, that means there is at least one number which is not equal to -1. So I just iterate over the array for int I equal to 0, I less than I plus. If b of I is not equal to -1, so that means we know b of I. So I just store that value in x. Like I just store b of I plus a of I as x. Right. Now I just check that for every element, okay, for every index, I have to ensure that bi plus ai is equal to this x that I found. Right. So if for int I equal to 0, I as I plus plus, if bi is not -1, so that means that I know bi. I know the value of bi. So I have to ensure that my bi plus ai has to be equal to x. So if it is not equal to x, then I just print 0. Right. That is if I know. And if I don't know bi, but if I don't know bi, then actually now I know bi because I know x now. So it is x minus a of I. So if x minus a of I is less than 0, that is when bi is less than 0, or x minus a of I is greater than k, right? Then that means that my bi is out of range. So again, I see out 0 and I return, right? But if all of the elements satisfy the conditions, then I just print 1 because I know the value of x and I can just determine the value of bi. So I just print 1 and return, right? So this was the case when I knew bi. I knew at least one value of bi, and let's say I don't know. Then what I just do is I just make these intervals. And what is an interval? Like the LHS is just AI. So I just showed you that AI is less than equal to x less than equal to AI plus k. This is my inequality, right? That's what I told you here, that bi should be between 0 to k, and since bi is x minus ai, so x minus ai should be between 0 to k, so x should be between ai and ai plus k, right? So these are the inequalities that you have to take the intersection of. So ai less than equal to x less than equal to ai plus k. So LHS is ai and RHS is ai plus k. So just take the maximum of ai. Like I just have ln r initialized to 0 and infinity. And then what I'll do for int I equal to 0 as an I plus plus, I just take L equals to max of L comma AI. So I'm taking the maximum value of AI, right? And R equals to min of R comma AI plus K. So I'm taking minimum value of ai plus k, and my final interval is basically L to R, right? So the number of elements in L to R is R minus L plus 1, right? So I printed that. And I actually printed 0 as well. Like I just took the max with 0 because I thought that maybe if the interval is empty, like if R is less than L, then in that case we would have to print 0. But I did not think about the fact that AI is also bounded till K. So that will never happen. Yes, I am doing intersection. Okay. So I think it should be clear now. So I'll go to the problem D. Flower boy. Flower boy has a garden of n flowers that can be represented as an integer sequence a1, a2 up to an, where ai is the beauty of the ith flower from the left. Igor wants to collect exactly m flowers. To do so, he will walk the garden from left to right and choose whether to collect the flower at his current position. The ith flower among the ones he collects must have a beauty of at least bi. Igor noticed that it might be impossible to collect M flowers that satisfy his beauty requirements. So before he starts collecting the flowers, he can pick any integer k and use his magic wand to grow a new flower with beauty k and place it anywhere in the garden, between two flowers, before the first flower or after the last flower. Because his magic abilities are limited, he may do this at most once. Output the minimum integer k Igor must pick when he performs the operation to ensure that he can collect m flowers. If he can collect m flowers without using the operation, output 0. If it is impossible to collect m flowers despite using the operation, output minus 1. Okay, so simply what we have is basically we have n flowers, right? We have n flowers of beauty ai. So first flower is of beauty a1, second flower is of beauty a2, third flower beauty a3, and so on. And the nth flower is of beauty an, right? And what we want to do is we want to pick m flowers, right? So what the constraints are is that let's say that I pick the first flower to be a3. This is my first flower. Like I did not pick these two, but I picked this one. So um, the constraint is that my a3 should be at least greater than equal to my b1. So I have also been given a b array, like b1, b2 up to bm, and we have to ensure that the ith flower that we pick has to be at least of bi beauty. Like the first flower that I pick, if I pick a3 as the first flower, then it has to be at least of b1 beauty. The second flower, let's say I pick a5, then my a5 has to be of at least b2 beauty, and so on, right? That is the constraints to pick up the flower. So I have to pick up these flowers. Now we notice that it might not be possible to pick up all of these flowers, right? So what we do is we can do one operation before we start collecting. Before we start collecting the flowers, we can do one operation that we can insert one flower, exactly one flower of value k anywhere in the array. Like here we can insert k, or here we can insert k, or here we can insert k, or even here we can insert k, and we can choose the value of k. The value of k we can choose, right? So the problem is asking that what is the minimum integer k to ensure that he can collect those m flowers, right? That is the problem here. So how do we solve this? Here the limits first of all are like m is less than equal to n less than equal to 2e5. So of course m less than equal to n should be there because there are only n flowers, and you have to pick up m of them, right? So and like the heights are up to 199, so the limits are pretty harsh. Like we cannot do n square n cube, right? So okay, now first of all, let's try to solve an easier version of this problem. Okay, like what I'm saying is, let's try to solve this problem if we are not allowed to do the operation. Like here we are allowed to insert one k element, right, anywhere in the array. But what if we are not allowed to do that? Then how do we check that is it possible to pick up m flowers or not, satisfying this condition? So how do we check that? Ahmed is saying two pointers. Or is he saying two pointers to my question? Or is it written beforehand only? Okay, Vijesh and Pradeep are saying two pointers. So yeah, that is correct. Like what you can just do is you can inherit a greedy approach. Like I'll take a test case where the answer is 0. Okay. So the answer is 0 in the fourth one. So 842.125.614. 842.125, and we have 614. So simply what we want is the first flower that we want to pick has to be at least 6, right? So we pick this one. Like we can pick this one, right? We can pick this 8. So it is no problem. So we'll pick this one, and we have picked the flower of 6. Now second flower that we pick has to be at least 1. So this 4 satisfies, so we can pick this floor. We can pick this 4, and we have picked it. And the last flower that we pick has to be at least 4. So of course we cannot pick this 2, and we cannot pick this 1. We cannot pick this 2, so we pick this 5. So finally we have picked 8, 4, and 5, and we did not need to insert any element into the array, and therefore the answer is 0, right? So actually this is a greedy approach, right? Like whenever I am seeing that my AI, like I have two pointers, right? Let's say I have two pointers, one in A and one in B. So in my array A, my pointer is I, right? So in my array A, I have the I pointer, and in my array B, I have the P1 pointer. Let's say, like this is my new. That's what I have named in my code. So that's why I am going with I and P1. So in A, my pointer is named as I, and in B, my pointer is named as P1. So what I'm doing is, every time my AI is at least equal to B of P1, then I'm definitely taking that AI. Like I'm taking this AI, and I'm doing it greedily approach. Like I'm doing it greedily. And why is it correct? It is correct because what you can simply do is, like, see, if it was not correct, then that means that we have another combination where, like, we are not taking AI. Like if this is not correct, then that means that we have another combination which did not take AI but took some forward elements. Like it took this one at P1. Like let's say we want to take the 6, right? So let's say there was a 7 also here. In this array A, there was 7 also. So let's say if my algorithm was incorrect, then it would not have taken 8, but it would have taken 7, it would have taken 2, it would have taken 5. So if I have this combination, then I can just remove the first element and insert AI into this. Since AI is also greater than equal to 6, right? So I can, instead of choosing this one, I can always choose this one. Because if this 2 and 5 are ahead of 7, then of course they are ahead of 8 as well. So I can always choose this 8 and get a correct answer. Like this proof was not very necessary, but this was the proof of this greedy approach, that we just take, like if my AI is greater than equal to B of P1, then I just take A of I. Right. So that is the approach where um, that is the approach that we can adopt. Like if we did not have to do an operation, but now that we have to do an operation, then what should we do? So okay, now actually my claim is that inserting some number k at the position a of I, like I had the array, right, a1, a2, a3 up to an, and if I insert k somewhere, let's say I insert k here, so that means in my array b, like I have b1, b2, uh, b3 and up to bm. So that means, see, if I'm inserting k, then obviously I'm taking k, right? So let's say my k has been taken by b2. So basically, one of bj, like one of the elements of bj, will be mapped to k, and the elements previous to bj will be mapped to the elements previous to k, like these elements, and the map and the elements after this bj will be mapped to the elements after this k, right? So essentially, what I can say is that if I delete this b2, if I delete this b2 and I run the algorithm here, like if I run the greedy algorithm on b1, b3, b4, b5 up to bm, if I run the algorithm on this new array, if I after deleting b2, then it is same as inserting k and running the algorithm, because you can see that, right? Because these b1 and b3 till bm are always mapped to a1, a2 and a3, an, and this b2 now has been mapped to k. So basically what I can do is I can just delete some element from b and check if it satisfies the constraint with a or not. My claim is that doing the operation of inserting k into the array A is equivalent to deleting one element from the array B. Like, why do I say that? See, I have this array A and I have this array B. B1, B2, B3, B4, B5, B6, and let's say B7. So if I delete B4, let's say, so my claim is that I can just delete any one of B and check my algorithm for the rest of the array B. Like this algorithm that I was doing here, I can just check for that, and if it is satisfying, then I can just insert this element. So why do I say that? Like let's say I delete this B3, okay, and I find some mapping. I find some mapping of A1 of these B1, B2, B4, B5, B6, B7. If I find some mapping to these A, okay, let's say B2 is mapped to A3, then B4 is mapped to here, let's say, then B5 here, B6 here, not to AN, like B5 here, B6 to somewhere before, and B7 to AN, let's say. So this is my mapping that I found using my algorithm. So what I can just do is I can insert the B3. Like I can just take my K as B3 and insert this K anywhere between these two, like where B2 is mapped and where B4 is mapped. I can just insert K between those two positions, right? So therefore, my operation of inserting K is equivalent to deleting an element and just inserting a flower equal to the value of that what I deleted. So if I am deleting this B3, so at least I have to insert a B3, right? Like if I insert less than B3, then of course I cannot map this B3 to that value. So I have to insert at least B3, right? So I can simply delete any one value of B and just insert that value into my array. And if the deleted array, like if my new array of B has some mapping, then I can say that one of the possible answer is B3. Like if I delete B3 and the remaining array B1, B2, B4, B5, B6, B7, if they have a mapping, a valid mapping, then one of my possible answers is B3. Like just remember what was my answer. Like what do I have to print? I have to print the minimum value of k. That is the minimum integer that I am inserting. So if I delete B3, then of course I have to insert this B, at least B3 into the array A. So if upon deleting B3, if I am getting a mapping using these elements, then I can say that one of the possible answers is B3. So one approach is this one, that out of all the elements B1, B2, B3 up to BM, let's say I try to delete them one by one. Like let's say I delete B1 and then I check whether B2 to BM has a mapping in the array A. If it does, then I'll just do ans equals to minimum of ans comma B1. Then I try to delete B2. So if my remaining array, which is B1, B3, B4, B5 to BM, if that is a mapping, then I'll again do ans is equal to min of ans comma B2 and so on. So that is my method. Like that will take O of n square, right? Because every time I am deleting an element and I am checking for the remaining array, and to check if there is a mapping or not, we are taking O of n, right? This my greedy algorithm is taking O of n, and I want to delete like m items. I want to try and delete m numbers. So it is basically O of m into checking. Actually, checking takes O of m plus n, in fact. O of n plus m. So final complexity would be m into n plus n. But that is too slow, right? So we cannot use that. So what do we do? Actually, we can extend this idea only. We can take this idea and extend it. How? Like, see, what I am simply doing is that I want to just check that does there exist any mapping an b1, b2, b3, b4, b5 and b6. So let's say I try to delete this b4 right here. Then I want to check whether there exists any mapping such that this b1, b2, b3 and b4, b5, b6 are mapped into the array. I want to check that, right? So like now how do we check that? Like we have to check that fast, right? So one idea is that we can independently check for this prefix and this suffix. Like what I am saying is that just check that, let's say I want to just map the elements from b1, b2, b3. Like let's say that this a1 is greater than equal to b1. Okay, this is the condition. So I can map this b1 to a1. Then let's say this a2 is actually less than b2, so I cannot map it here. So let's say I can map b2 to a3, and then I can map b3 to a4. Okay, so this is how I can map this b1 to b3. And now let's say if I want to map, let's say b6, let's say I map it to an, and this b5, like if I want to map both b6 and b5, then let's say I cannot map b5 to an minus 1. Let's say I cannot map b5 to an minus 2. Let's say I have to go to a3. Like if I just want to map b5 and b6, so let's say I can map b6 to an. So I'm going in reverse. Okay, like I'm going in reverse, and if I want to map this b6 to an, and then I want to map this b5, so what can I map it to? Like let's say I cannot map it to these numbers because they're all small. They're all less than b5. And the first number that I can map to is a3. Let's assume this. And if I want to map these b1, b2, b3 to a1, a3, and a4, like that is the minimum that I can do. If this is the case, that to map these b1, b2, b3 to a1, a3, a4, that is the that is the minimum index. Like a4 is the minimum index that we can map to if we want to map b1, b2, b3. And if we want to map b6, b5, then if I have to go till a3, then that means that it is not possible to map these b1, b2, b3 and b5, b6. Conversely, if I say that, let's say for an example, if we have a1, a2, a3, I'll just take n equals to 8 for now, and b is equal to m equals to 5, let's say. So b1, b2, b3, b4, and b5. So let's say that I know, let's say I want to delete b3, okay, and let's say that I know that to map just b1 and b2, I have to map them to, let's say b1 has to be mapped to a2. Like let's assume that a1 is less than b1, okay, so and a2 is greater than equal to b1. So b1 has to map to a2, and then b2 has to map to a4, let's say. So that's what b1 and b2 have to map to. And let's say we also know that to map this b5 and b4, we have to map b5 to a8 and b4 to a7. Like we know that to map the first two elements, we would have to map them to a1 to a4, and to map the last two elements, we would have to map them to 7 and 8. Then that means that I can simply map these four elements as well. Like if I want to map these four elements together, then I can do that, because I can just map b1 to a2, b2 to a4, b4 to a7, and b5 to a8. And why is that? Because this index, like this a4 index is less than a7 index. So since 4 is less than 7, therefore I can map. Like if I know the conditions that to map b1 and b2, I need to go at least till 4, and to map b4 and b5, I need to come at least till 7, right? Then I can say that I can map b1, b2, and b4, b5. But in this case, I said that to map b1, b2, b3, let's say I need to go at least till 4, and to map b5, b6, I need to go at least till 3. So now they're kind of overlapping. So since this 4 is greater than equal to 3, like 4 is not less than 3, so therefore we cannot actually map b1, b2, b3, and b5, b6. Again, okay, so I'll tell you an example. Okay, so let's say we have a sample test case, which is this one. Okay, or let's take second one only, 126,821, and 543. So okay, now just notice that if I want to map 5, then I will have to go at least till this index, because I cannot map it to 1 or 2, right? Then I want to map 4, so I'll have to go at least till 8. And if I have to map 3, then actually I cannot map it, right? So that is the prefix that I'm storing. And if let's say the suffix, if I store, like this is what I have stored, that to just map 5, I have to go till 6, and to just map 4, like to map 5 and 4 both, I have to go till 8, right? But now let's see the suffix, like 1 2 6 8 2 1, and 5, 4, 3. So if I want to just map 3, then of course I cannot map it to 1 and 2. So I have to map it to 8. So to 3, 3 I have to map to 8. Now this 4 I have to map to 6. And now this 5 I cannot map to anything. So this is my suffix that I have stored. So now let's say that I am checking that can I see what we are doing is that we had this B array, right? We had this B array which was 5, 4 and 3. And we could delete some elements from this B array. So what we are trying to check is that is it possible to map it if I delete the element 5. Okay. So let's say I deleted the element 5. Then is it possible? So yes, it is possible because I can definitely map the elements 4, 3 to 6 and 8. So I can just put 5 somewhere behind 6 and 8. Like this 4 and 3 are mapped to this, right? So I can just put a 5 somewhere and I can map 5 to there. So definitely 5 is possible. Then is 4 possible? Like is it possible that I delete the 4 and this 5 and 3 are mapped? So let's check. So what I'm doing is that before this 4 there's a 5, right? So to just map this 5, till where do we have to go? Just check that. Like to map this 5, we have to go till 6, right? We have to go till 6 on this index. And to map this 3, to just map this 3, we have to go till 8, right? And 6, and since 6 is before 8, since 6 is before this 8, I can simply map this 5 to this 6 and this 3 to this 8, and I can put like a 4 in between those and map it to there. So generalizing, what I am saying is that if I have B1, B2, B3, B4 and B5, and let's say I want to delete B3, okay. So if I already know that in order to map B1 and B2 into my array, let's say I already know that in order to map this B1 and B2, like just these two elements into my array, I would have to go till A4. Like if I know that I can go till A4 and map these two elements, and if I already know that if I just want to map these two elements, then I have to go till, like let's say I can map this B5 to A7 and B4 to A5. Like this is my maximum mapping. Like this is the rightmost that I can be to map these two. Like if I already know that I can map these two just by going till index 4, and I can map these two just by coming back till index 5, then I can say that I can map all of these 4. Like I can map B1, B2, B4, B5 simultaneously by mapping, just combining those, right? Like A2, A4, A5, A7. So since this last index of my prefix, like this is my prefix, right? Like what I am trying to delete, the left of that is its prefix and the right of that is suffix. So um, to delete this or to map this entire prefix, I have to go till 4. And to map this entire suffix, I have to come till 5. And since 4 is less than 5, that means that there is no overlap. Like there is no intersection like this. Like let's say I had to, like let's say that A7 is less than B5, A6 is also less than B5, A5 is also less than B5. So I had to map A5, like B5 to A4 if I wanted to map B5, and I have to map B4 to A2. Like if that is the best that I can do, then that means that on the prefix I have 4. On the prefix I have this index 4, that to do the prefix I have to go till 4, and to do the suffix I have to come till 2. So there is overlap, right? these arrows are crossing. So definitely I cannot map these elements simultaneously. So 4 is not less than 2, and that's why we are not able to map the prefix and suffix simultaneously. So like Ahmed, do you get it now? So what I'm just storing, like what I can just store is that for every prefix, like let's say I have my wait, what just happened? Let's say I have my B1, B2, B3, B4, and B5. So to just map this B1, till where do I have to go? Then to map B1 and B2, till where do I have to go? Then to map B1, B2, B3, till where do I have to go? To map these four elements, where till where do I have to go? And to map B1 to B5, till where do I have to go? So we can just store that. Okay, like till which index do I have to go? We'll store that. And also what we'll store is, if I just want to map B5, then what is the rightmost that I can go? Then if I want to remove B4 and B5, then also what is the rightmost that I can go? Then B3, B4, B5. So all of these values, like of all the prefixes and all the suffixes, I'll store beforehand. And then what I'll do is, I'll just try to delete all of the elements. Like in the array B, I'll try to delete all the elements. Like I'll try to delete B2, I'll try to delete B3, I'll try to delete B4. And I can delete them if and only if the remaining elements can be mapped, right? Like I can delete this B3 if and only if this B1, B2, B4, B5 can be mapped in the array. And when can it be mapped? It can be mapped only if this B1, B2 are answer. Like let's say the furthest that I have to go, like the rightmost that I have to go, like to map this B1. So B1, let's say I map to A1, and B2, let's say I map to A5. So this is 5 for the prefix. And let's say have to map B5 to A10 and B4 to A7. So my B4 is 7, like the suffix is 7. So if the prefix is less than the suffix, or I can say that if the prefix value of I minus 1 is less than the suffix value of I plus 1, then I can delete the ith bi. So I can delete bi, and since I'm deleting bi, or essentially I'm inserting bi into this array, so therefore I'll take, like my value of k is bi in this case. Like if I want to delete this bi, then my value of k would be bi. Okay, so that is the solution here. Let's just try to show this on a test case. Like I'll show this on this test case to give more clarity. So we have 35233 5812. And the second array we have 46246. So I'll just index these. Okay, I'll index these. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8. So my S array, like I'll make two arrays, P and S. So P array means that let's say this 4, if I want to map, so till where do I have to go? If I just want to map 4, then I'll have to map till this 5. So this will be 1. Then if I want to map this 4 and 6, so I cannot map 6 to here. Then I cannot map 6 to here. So where can I map 6? I can map 6 to this index. So the P of 6 will be 8, or P of this value will be 8. Then if I want to map 2, and I can map 2 to this 8. Sorry, the index is 6, right? The index is 6 and here the index is 8. And now of course I cannot map 4. So let's say it is infinity and infinity. Okay, so that's how I make the prefix. And wait, and let's say I make the suffix also. So if I want to map 6, then I have 8. So so I have to go till 6. Then if I want to map 4 also, I have to go till 5. So I have 5. Then if I want to map 3 or 2, I can go map to this 3. So I have 4. Then if I want to map this 6, then I cannot map it to anything, right? So essentially it will be minus infinity and minus infinity. So like I'll have to go till minus infinity essentially, right? So now what I can just see is that, can I delete this? Can I delete this? No, I cannot delete this because I cannot map these elements. Why? Because this is minus infinity, right? So I cannot delete this 4. Okay. Can I delete this 6? I can delete this 6 because this prefix, this 1, is less than suffix, which is 4. Since 1 is less than 4, I can delete this 6. Can I delete this 2? So there is 6 and 5. So no, I cannot delete this 2. Because when I try to map 4 and 6, like when I try to map 4 and 6, so what will happen? I will map 4 to here and I will map 6 to here. Or let me just use another color. When I try, why does this happen? Do you guys have any idea why I'm not able to select this color and not even any of these pens? I'll have to restart with this one note. So if anyone of you has any idea why it is happening, so just let me know. Alright, anyways, so I was saying that if I want to delete this 4, or sorry, this 2, then I cannot do that. And why? Because when I try to map this 4, I'll have to do it with 5. And try to map this 6, then I have to do it with this 8. And when I try to map the suffix, sorry, the suffix, then this 6 I'll have to map to this 8, and that is a contradiction because I have already used up till here in mapping this 4 and 6, so I cannot do that. And in short, what I can say is that since this prefix is not less than suffix, so this 6 is not less than 5, so therefore we cannot delete 2. Then can we delete 4? No, we cannot delete 4. Or can we? Wait. No, we cannot delete 4 because this prefix, like prefix of 4 is 8 and suffix is 6. And since 8 is not less than 6, we cannot delete 4. And can we delete 6? Can we delete 6? We cannot delete 6 because then we would have to map this prefix, but the value is infinity, so we are not able to map this prefix. So essentially we are only able to delete this 6. So the only way is to delete this 6, and therefore the answer is just 6. All right. Okay, Kavish, edge case, like -1 case will be happening when we are not able to delete anything. And okay, and first of all, when will 0 come? Like 0 will come when we are able to map the entire prefix to the array. Like if the last value is not infinity, or if the first value in the suffix is not infinity or minus infinity, then your answer will be 0. And your answer will be -1. -1 if you are, like if your prefix is in infinity, like you are not able to map the entire thing to the array, and also you are not able to delete anything. Like for all the indices I, my prefix of I-1 is not less than suffix of I+1. like for all the indices. If this is there, then that means that I cannot delete anything, and I also cannot map the entire thing to my array. So therefore, the answer is -1. Okay, so I did everyone of you got it? I mean, get it? Okay, so I'll show the code now. So I have int nm c in nm, input the array a, input the array b, and I make two arrays s and p, which are suffix and prefix, and I initialize them to -infinity infinity. So as you can see that in the prefix, I'm initializing them to infinity, and in suffix to -infinity. And why am I doing that? Because I want that p of I minus 1 is less than p of s of I plus 1, right? And if any one of them is not valid, then I want it to be false. So if I set p of I minus 1 to be infinity, then whatever there is here, this will not satisfy. And that's what I want. So that's why I am setting it to infinity. And here I am setting -infinity because that's what I want, that s of I plus 1 should, like, you get the point, right? Then I have, like, I'm initializing these two arrays here. So in this block, I have initialized the prefix array, and in this one, it's the suffix array. So how I done that? Like, um, p1 equal to 0. So my pointer on the b array. Okay, this is the pointer on my b array, and I just iterate over the a array. For int I equal to 0, I less than I plus plus. If p1 greater than equal to m, then break. So that means that we have already mapped all of the elements. So we just break. Okay. Now if ai is greater than equal to b of p1, right? That means that we can map our b of p1 to a of I. Like, that's what we will greedily do, right? Like, as you can see, if my um, b of p1 is greater than a of I, sorry, less than equal to a of I, then I can map this b of p1 to my a of I. So that means that for the prefix p1, like, to map 0 to p1 in b, like in b, to map 0 to p1, I have to go till I. Like, since I'm mapping this p1 to I, that means that to map the entire prefix from 0 to I have to go till I. So p of p1 is equal to I, and then I just increment the p1 pointer because I have mapped till p1. So I just increment it. All right. So that's how I create the prefix, and in similar fashion I create suffix. That is, I just start this p2 pointer to the last. Like, I just initialize it to the last, and also I iterate the array a in reverse. So for int I equal to n minus 1, I greater than equal to 0, I minus minus. If p2 is less than 0, then break. If p2 is less than 0, then break. Why am I doing that? Because if p2 is less than 0, that means that we have already mapped 0 as well. So we are starting from m minus 1, and we have mapped till 0. So we just break at that point. Now if ai is greater than equal to b of p2, then that means we can map our b of p2 to a of I, and therefore for our suffix, like from p2 to m minus 1, we needed to go till I. So s of p2 is I, and p2 minus minus. Now if p of m minus 1 is not equal to infinity, that means we are able to map the entire prefix, or basically the entire array b, onto the array a. So we don't need to insert anything. So I just say out 0 and n line and return. Now I just iterate over all of the elements from, like, b, all of the elements in b, and try to delete them. So if my I is equal to 1, I less than n minus 1, I plus plus. So I'm trying to delete this b of I. So if s of I plus 1 is greater than p of I minus 1, then I can delete b of I. So I'll just take ans equal to min of ans comma b of I. So that's what I'm doing. Like B1 to B of n to B of m minus 2, I've checked here, like the middle indices, and the first index I can delete if my s of 1 is not equal to minus infinity. Like what I'm saying is that if my, like, I have B0, B1, B2 up to Bm minus 1. So I can delete this B0 if I'm able to map this entire array onto somewhere. So if I'm able to map the suffix of 1, like if I'm able to map this s of 1, like if s of 1 is not equal to minus infinity, then I can delete this B0, right? And what about B and m minus 1? So if I'm able to map these first elements, like if I'm able to map these elements into my array A, then I can delete this, and that means that my P of m minus 2 would not be equal to infinity. So if it is not equal to infinity, then I can also take the minimum with B of m minus 1. Now, if my answer is still equal to long max, like I initialize it to be long max, which is basically infinity, then I'll see out minus 1, because I am not able to delete anything, and also I did not see out 0 here, so I'll see out minus 1. It is not possible. Otherwise, I'll just see out the minimum value of bi, which is my answer that I need to insert here. All right, so that's the solution, and I hope it is clear. So if someone has a doubt in the code, then they can ask me. I'll wait for 10 seconds. Okay, so I think it is clear. So I'll move on to the next one. So I have this one, which is E. Wolf has found n sheep with tastiness values P1, P2 up to Pn, where P is a permutation. Wolf wants to perform binary search on P to find the sheep with tastiness of K, but P may not be sorted. The success of a binary search on the range for K is represented as f of L, R, K, which is defined as follows. If L greater than R, then f LRK fails. Otherwise, let M equals to L plus R by 2. And if PM is equal to K, then f LRK is successful. If PM is less than K, then f LRK is equal to f M plus 1 RK. If PM is greater than K, then f LRK is equal to f L M minus 1 K. Cow and the nerd decides to help Wolf out. Cow the nerd is given Q queries, each consisting of 3 integers L, R, and K. Before the search begins, Cow the nerd may choose a non-negative integer D and D indices 1, so I1, I2, ID, where we cannot choose the kth, like we cannot choose the index where it is K. Then he may reorder the elements however he likes. For each query, output the minimum integer D that cow the nerd must choose. So f of LRK can be successful, or report that it is impossible. Note that the query is independent and the reordering is not actually performed. Okay. So yeah, the problem here is that, like, they have framed it in a very mathematical way. I'll just tell you that what it means. Okay. So what they mean is that we have a permutation. We have a permutation of 1 to n. Okay. So we have P1, P2, P3 up to Pn. So we have these numbers from 1 to n, and what we need to do is we need to binary search for the value of K. All right. So like we are given Q queries, right? We are given Q queries, and we have to do binary search in the range L to R. for the value of k. And the method is the same. That how do you do binary search? You simply just look at the middle element. Like you have PL, P of L plus 1 up to PR, right? So you will check P of L plus R by 2, right? So if it is if it is equal to K, then it is successful. You have found the element. If it is, let's say if it is less than K, then what you will do is you will check in the range of M plus 1 to R. Like this is M. Let's say this is M. Then you will check the range M plus 1 to R if it is less than K. And if P of M is greater than K, then you will check the range L to M minus 1. Right. So this would work if P was sorted, right? Or if the subarray PL to PR was sorted. But it doesn't work now because it is not necessarily sorted. So how do we, like, now we have to check that will it reach K eventually? Like, will our binary search reach K? And if it does reach K, like, okay, and we are also allowed to do some rearrangements. Like, we can choose some indices in P, okay, and we can shuffle them. Like, let's say I choose K indices. Like, let's say I choose K indices I1, I2, I3 up to IK. Then I can shuffle these indices. Like I can shuffle PI1, PI2, PI3 up to PIK. Like shuffling means that I can rearrange these values in any way I want in the permutation. Right. So what we have to tell is that what is the minimum number of elements that I have to shuffle. So to ensure that my binary search, which starts from LRK, ends up finding K, right? Even though P is unsorted. And actually, I cannot choose the index which has P of I. Like I cannot choose an I such that P of I is equal to K. Like I cannot choose this index. It is not allowed. Like all of these indices that I have chosen have to be not equal to the value that I am doing a binary search on. They cannot be equal to this value, because then of course I could just swap that element with the position where the binary search ends on. Or maybe I can just, like, if I have like L, R and K as my query, then I would just do what? I would just exchange the indices L plus R by 2 and the index of K. Like let's say Pi of K means the index of K. So I would just exchange these two indices. So the first index that I check would be equal to K, and it would stop there. So always my answer would be 2, or it would be 0. 0, it would be when like it would be 0 when we are anyways landing up on K. So in that case, the answer would always be 2 or 0. But we are not allowed to move the K. We are only allowed to move other elements. And we have been asked that what is the minimum number of elements that we have to move. All right. So let's have a look at the test cases to get a better understanding of the problem. So let's say 1, 2, 3, 4, 5. This is a bad test case. 3, 1, 5, 2, 7, 6, 4. Okay, so 3, 1, 5, 2, 7, 6, 4, and we have 3, 4, 2. Like let's say we have this test case 1, 5, 6, or not 1, 5, 6. Let's say we have 1, 7, and 3. Like my L equals to 1. r equals to 7 and k equals to 3. And basically we are not allowed to move this 3, right? We are not allowed to move this 3. We can move any other element that we want. So what will happen in this binary search? Just think that. So the indices are what? Like I'll index this again. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So first of all, what I'll do is I'll go to this index 4, right? And since this P4 is less than K, then I would go to the right. I'll search in this one. But that is a big problem because my 3 is actually here, right? So we want that definitely my binary search should go to the left. Like what I want is that my binary search should go to the left. It shouldn't go to the right. Right. So I have to definitely change this 2 to something else. Like I have to change this 2 to something which is greater than 3. Something greater than 3. Okay. So that is one thing. So I'll mark that. Okay. I'll mark this 2 that I have to change this 2 to something greater than 3. So now that, like, let's say I have something greater than 3 here. So when I check this P4, it would be greater than K, right? So now I'll check in this subinterval. So the middle element is what? 1. So if I check 1, that is P of 2. P of 2 is also less than K here. So what we would just do is search in this range now. In this range. But what I want is that I want to go left because my 3 is actually there. So also this index also I want to ensure that it is greater than 3. Right. And finally, if it is greater than 3, then finally I'll end up here. I'll end up at this position and it will definitely be 3. Like that is 3, so I can stop there. Right. So essentially what I want to do is that I want to replace this 1 and 2 with some numbers which are greater than 3. Right. So what I can just do is, let's say I replace this 1 with a 5. So I swap this 1 and 5 and I swap this 2 and 7. Okay. So what does it become? It becomes 3, 5, 1. 2, sorry, 3, 5, 1, 7, 2, 6 and 4. This is what it becomes. So as you can see that here the first comparison that I make, that is greater than 3. So I'll go to the left. I'll go in this array. And this comparison also results me going into the left. So I'll end up at 3. So since I moved 4 indices, like as you can see that I moved this index, this index, this index and this index. Therefore my answer is 4. Right. Like of course I cannot make more than 3. To make more than 3 here and here, of course I would have to move 2 other elements as well. Like see, obviously I'll have to move 1 and 2 also. Like I want to make um, this index and this index greater than 3, right? Both of these greater than 3. And both of them are less than 3. Both of them are less than 3. So of course I would have to choose 2 other indexes which are greater than 3 and just swap them. So definitely my answer is 4. So therefore the answer to this test case, the last test case of this second one is 4. Right. That is the thing here. So that is actually the algorithm. Like what I just showed you is actually the algorithm that we are going to do. Okay, like we are just going to perform the binary search and we are going to check our requirements. Like what does that mean? That basically, let's say we are doing a BS on AL L plus 1 up to AR. Now, first of all, if in this range my value K is not present, then just print minus 1. Just see out minus 1 because my value is not present in this array and I cannot move that value. So, of course, I cannot make it in this array. So, just print minus 1, obviously. Now, let's say it is present. Okay. So, what we'll do is we'll simulate a binary search. Okay. So we have this ln r. So we'll compute m, where m is equal to L plus r by 2 GIF. And what we'll do is we'll check am. Okay, we'll check am. So if my am, now there are two cases, right? Actually, yeah. So there are two cases. Wait. Again, it is facing the same problem. So yeah, what I'll do is I'll compute this m and I'll look at am. So now there are actually two cases that, okay, let's say that the index of k is c, like my p of c is equal to k, and this c is between L and R, right? So my p of c is k. So now if my, there are two cases that, actually there are three cases, like if m equal to c, like if I have reached this k, then I can just break, like out of the simulation I can break, right? But what if m is greater than c, right? Then we have to go left. We need to go left, correct? So what does that mean? That means we need that am should be greater than k, right? So at the mth position we need the number to be greater than k. So what I'll do is count the number of positions where I need am greater than k. So I'll maintain a counter. Okay, I'll maintain a counter which will be called GC, like greater count, which will store the number of indices I, the number of indices I, such that I need such that I need AI to be greater than k. Okay, so this is the GC. Like maybe my variable name in my code is different, so let me just check what is the name in the code. Just 1 minute. I'll use that name what I have used in my code. So yeah, down and up. So I am just maintaining a counter called up and down. So my up means the number of indices I, such that I need AI greater than k. That is called up. So let's say that m is greater than c, then I'll increment this up variable. Like wherever I see m greater than c, so I'll increase my up variable because I want that am is greater than k. Okay. And I also have another variable called down. Down is equal to the number of indices such that I need a of I to be less than k. Right? So let's say if I land at m, like if I land at m and if m is less than c, that means in our binary search we need to go to the right. So that means we should have a of m less than k, right? So if we should have a of m less than k. So that is the number. So I'll store that in down. Like that is the number of indices such that I need a of I less than k. Okay. So now, as you remember that we have permutation, right? Like we have permutation from 1, 2, 3 up to n, and we have a k somewhere in between. So the elements less than k, how many are there? The elements less than k are k minus 1. Like we have k minus 1 elements which are less than k, and we have n minus k elements which are greater than k. So these are less than k and these are greater than k. The number of elements in the entire array. So this is my up and down variables, right? My up is the number of I such that I need ai greater than k. I need ai greater than k. So if my number of elements, or like the number of indices where I need ai greater than k, if that is at most n minus k, like if up is less than equal to n minus k, that means that I can definitely have it satisfied. Like I can just place out of this n minus k variables, I can just place up number of numbers onto the indices where I need that ai is greater than k. Like I'll just choose up number of numbers to put in these indices I. And since there are n minus k numbers which are greater than k, and if up is less than equal to that, then I can do that. And also I need that my down is also less than equal to k minus 1, because I need that, like at down number of places I need that ai is less than k. So that can only happen at max k minus 1 places. So therefore I need that down should be less than equal to k minus 1 and up should be less than equal to n minus k, right? So if this is satisfied, then definitely I can do that. I can definitely rearrange my array such that this is satisfied and I end up at my k, right? So that's why in this case the answer will not be minus 1. Answer will not be minus 1. And if any one of these is greater than that, like if up is greater than n minus k or down is greater than k minus 1, then I will say that answer is minus 1, because I need, like let's say I need down number of indices such that a less than k, but there are not enough numbers which are less than k, so of course I cannot make them. So in that case the answer is minus 1. So is it clear till here, guys, that how will I know whether my answer is minus 1 or not? So is it clear till now? Guys, just tell me that is it clear? I'm not getting a response, so I'll assume that it is clear. Okay. So yeah, up is less than equal to n minus k, down is less than equal to k minus 1. If these two are satisfied, then I can definitely say that I'm able to make those indices as I want them, right? But now, how do I calculate the minimum number of changes that I have to make? Like that is my answer, right? My answer is that what is the minimum number of changes that I have to make, right? So while I am iterating, like while I am sending this binary search, just store more things. Okay, like let's say that we calculate this m, okay, and if m is greater than c, then we need to go left. That is, we need am greater than k. So we just increment this up variable. We do up plus plus. right? But let's say that we don't have a number which is greater than k. Like, of course, am is not equal to k, right? That we know because it is a permutation and k is somewhere else. So this one is not k. So we can say that am is either less than k or greater than k. So let's say that am is greater than k already. Okay. Then that means that I don't have to change it. Like, I don't have to change it, so I won't change it, right? If I don't, if it is working, then don't touch it. That's what I learned in the last PCD. So um, I won't change this. If am is already greater than k, then I won't change it. And if am is less than k, right? If am is less than k, then we need to change this. So we need to make this less than k to greater than k. Like, we need to change this less than k to greater than k, right? So just keep a counter. So let's say this is TD, wait, or TU. Like, I'm giving another counter, which is called TU, which stores that the number of indices where I have less than k and I want to make it greater than k, right? That is the number of indices where I have less than k but I want to make it greater than k. That is TU. So I'll just increment TU if my AM is less than k and I want it to be greater than k. Okay. So I'll increment TU, and if M is less than C, then I want my AM to be less than k. But if it is already by default greater than k, if AM is greater than k, then I will have to change, like, uh, this greater than k to less than k. Like, I'll have to swap it with something which is less than k. So TD, I'll increment this counter called TD. So TU means to up, like to upper half. TU means to upper half and TD means to lower half. So, like, I want to convert this lower half to the upper half, and I want to convert this upper half to the lower half. Upper half to the lower half. So that's what the naming convention is. And I'll keep a count of that. That how many indices there are, which I want to convert to upper half and to lower half. So now I have these four counters, like up, down, TU, and TD. So now if I have sufficient number of integers, that is up is less than equal to n minus k and down is less than equal to k minus 1, then I can definitely say that my answer is not equal to minus 1. But then what is my answer? Let's think about that. Like, to get my answer, so to get my answer, I can use these two variables called TU and TD. Like, what is TU? TU means that the number of variables, the number of indices rather, the number of indices where we have AI less than k, but we want AI to be greater than k. That is TU, right? And the TD is opposite, right? So what you can actually do is just pair some TU and TD. Like, let's say you have four indices where you want, like, okay, let's say your TU is, let's say your TU is equal to 4 and TD is equal to 2. So let's say, for example, my K is equal to 10. Okay. And here you have a 3. Here you have a 6. Here you have a 12. Here you have a 15. And here you have a 2. And here you have a 7. Right. And basically you want this 3 to be greater than 10. Like, at this index you want to be greater than k, at this index you want to be greater than k, less than k, like at this index you want it to be less than k, at this index you want to be less than k, greater than k, and greater than k. So what will you do? Like basically this is your tu, these four are your tu. So at these four indices you want that there should be something greater than k, and at these two indices there has to be less than k, so td. So what you can do is just pair some tu and td, like you can pair these two and swap them. So you will get 3 here, here 3 will come, and here 15 will come, and here 12 will come, and here 6 will come. So since you wanted less than k at in this index and less than k at this index, and you have here and you have that, and on these two indices you wanted greater than k and you have that. But okay, now what about these two indices? You want a greater than k here, you want greater than k here. So now what will you do? You will choose something else. Like, of course, this is not your whole array, right? Like, since you have enough number of numbers, like you have already checked that up is less than equal to n minus k and down is less than equal to k minus 1. That means that you have enough numbers to satisfy this. So what you have to do to satisfy these, you will have to find two other numbers in the entire array. Like these six indices are my indices which I want to change, but there are some indices which I don't care about, where there can be anything. Like during the binary search, I am not even checking them, so I can just like take them and swap them with this. So like, of course I have to choose this, and let's say I have some index where there is 20 and where there is an 18, so I can just swap this 2 with 20 and 7 with 18. So essentially I am pairing some tu and td, and for the remaining tus I am pairing with external. So you can verify that I am definitely taking 2 into max of tu and td. These many indices I am changing. Like because just take the max. Like let's say out of tu and td, tu was the maximum. So you had 4 tus and you had 2 tds. So out of these 4 tus, you just use 2 of them with this td, and the other 2 you used with some anonymously. Like you used with something else which was not tu or td. So you use these two and these two. So you have sorry, yeah, you have 8. So you have 8 indices which you want to change, and that is your max, 2 into max of tu comma td, and that is your answer. All right, I hope it is clear. So if you have any doubt, then you can ask me right now. This is your entire solution. That just check that at what index you want which condition, and to satisfy that, just count that how many, which type you want how many times, right? So Rizwan is asking the rating of this problem. You can do C list for that. And meanwhile, if someone has a doubt in that, then they can ask me right now. So this problem um, was rated. This is the thing, right? Wait, not this one. This problem was rated 1785. So which is around 1800, you can say. Okay. So yeah, if anyone has a doubt in this, please ask me right now. You all don't have a doubt, then I can explain the code now. But so I'm assuming you don't have a doubt since I am not getting any comments. Okay, so n comma q, c and nq, vector LL a of n. For int I equal to 0 less than I plus plus c in ai, vector LL pos of n plus 1. So I am storing the position of every element. So for int I equal to 0 I less than I plus 1, I less than I plus plus, pos of a of I is equal to I plus 1. Right. And then the queries I am handling while q minus minus LL LRK C in LRK, LLC is equal to pos of k. Right. So if C is less than L or C is greater than R, that means it is out of range. So I'll print -1 and then I'll continue. Now I have these four counters called down, up, TD and TU. So I'll just do the binary search. So while true, M is equal to alpha by 2. If C is equal to M, then we break. If C is greater than M, alright, and A of M minus 1 is greater than K, then down plus plus. That means we want that this A of M minus 1. Wait, I think I just changed the order. Like what in the explanation, what I said was down and up. They were TU and TD. I mean TD and TU. So like just assume that this code has different meaning of down and up rather than TD and TU. So I'll change the code when I send the submission link. But yeah, what I explained was the opposite. So down means TD here and up means TU here, and TD means down and TU means up. Okay. Anyways, so if this is the case, then I want two up. Like if C greater than M, that means I want to make A of M minus 1 less than K. So TU plus plus, sorry, TD plus plus. And if C is less than M and A of M minus 1 is less than K, then TU plus plus. If C greater than M, then my down plus plus and L equals to M plus 1. Else my up plus plus and R equals to M minus 1. Now if TD is less than equal to K minus 1 and TU is less than equal to N minus K, that is my down is less than equal to K minus 1 and up is less than equal to N minus K. So I have this condition right here. So I'll print this 2 into max of TD comma TU. Right. And otherwise I'll print -1 because it is not possible. And I'll see out endl after the test case ends. Okay. So I think the code should be clear. And now I'll quickly move on to the next one. Okay. So now we have problem F. Just 1 second. All right. So the last problem, which is F, that we are going to discuss today. Dr. TC has a new patient called Goblin. He wants to test Goblin's intelligence, but he has gotten bored of his standard test. So he decided to make it a bit harder. First, he creates a binary string S having n characters. Then he creates n binary strings A1, A2 up to AN. It is known that AI is created by first copying S and then flipping the ith character. After creating all the n strings, he arranges into an n by n grid where g of ij is equal to a of ij. A set S of size k containing distinct integer pairs x1, y1, x2, y2 up to xk, yk is considered good if um, 1 is less than equal to, so basically they are in the range of 1 to n, and g of xi y is equal to 0 for all I, and for any two integers I and k, we can reach from xi yi to xj yj by traveling through a sequence of adjacent cells that all have a value of 0. Goblin's task is to find the maximum possible size of a good set S. Right? Because Dr. TC is generous, this time he gave him 2 seconds to find out the answer instead of 1. Goblin is not known for his honesty, so he asked you to help him cheat. So basically, we have the same problem as A. So, right, uh, 1 minute. Yeah, anyways, so what I was saying is that the problem the problem says that we have a binary string, okay, a binary string of length n, which is like s1, s2, s3, s4 up to sn. All right, and like this is the one binary string, okay, like s1, s2, s3 up to sn. That is one binary string s, s1, s2, s3 up to sn. Okay, and what we have done is we have made a grid by just writing this s. Okay, like we just wrote this s n times. So we wrote s1, s2, s3 up to sn. Then again we wrote s1, s2, s3 up to sn, and till the end we again wrote s1, s2, s3 up to sn. And then what we did was that we flipped the diagonal elements. This diagonal element, we just flip it, right? So this is the matrix that we have created. So now what we have to do is that we have to print the size of largest connected component of zeros. Like this is what we have to do, right? Print the size of largest connected component of zeros in the grid, right? So it kind of seems like very much like a graph problem, right? Like what I'm saying is that this problem seems very much like a graph problem. Like we are given a grid and we need to find the connected components of zeros. So what can we do here? So let's say it was a typical graph problem and we like try to solve it. Then how would we solve this? How would a random person solve this even if they were trying to do it? Like we are just given an arbitrary grid, let's say of zeros and ones. 100, 10, 0, 0, 1, 1, 0, 0, 1, 0, 0, let's say 1, 0, 1, 1, 0, 1, 1. Or okay, yeah, so let's say that we need to find the biggest component of zeros. So here the answer would be 3, right? Because this is size 3, this is size 3, this is size 1, this is size 2, this is size 1. So the highest is size 3 and this size 3. So the answer is 3 in this case. So but like how would you solve this? Just think about that. So the way I would solve this is that I would use DSU, right? I would just use DSU. And how to do that? Like what I would do is just iterate over all the cells. Okay, like I iterate over all the cells, and let's say I'm at this cell. Okay, so whatever my neighbors are there, like this neighbor, this neighbor, this neighbor, and this neighbor. Like if current cell is 0, like then I'll do that. Like then I'll do that. If this current cell is 0, then I'll iterate over all its neighbors. And if that neighbor also is 0, if that neighbor also 0, then I will just join them. Like those two DSUs, I will unite them, or basically I'll add an edge between those two, right? So in the DSU, I will unite them, and I will do this for all of the vertices or all of the cells. So in that case, my biggest component that I would get would be my answer, the size of the biggest component. But now, how do we do this in this problem? Like, if we just do that, like if I make the grid and find out the size of the greatest component, then that will go to O of n square, right? Because the string is of n length and the grid will be of n square size, so it would go out to be O of n square, which is not passing. So since n is up to 2e5, it will not pass. So instead, what we can do is we can make an observation, right? Like since this grid is not arbitrary, it is made by some string. It has some definite patterns. Like since it is made by a string, it has some definite patterns. And what are those patterns? Just check it out. Like let's say I have some string, which is wait, is 1 1 0 1 1 0. Let's say. So if I make the matrix using this string, so let's say I do it. So it would become 1 0 1 1 0 1 0 1 1 0 1 0 1 1 0 and 1 0 1 1 0. So this becomes 5 times. And if I flip the diagonal indices, let's say I flip them. So what would it become? It would become 0 1 0 0 1. Okay. So this is the grid that you have formed. So for this thing, the answer would be what? For this thing, the answer would be just this, right? Like this has size 5, and this has size what? 4. This has size 2. So definitely the answer is of size 5, right? But how do you calculate that? Now actually, in this case also you can use DSU, but there is one observation. What observation is there? You can simply observe that how does a column behave? Like in our final grid, how does a column behave? Like how does a column look like? What does a column look like? Like let's say this is column I, right? This is the column I. So since I have made this from all S, like I have written S here, S here, S here, S here, S here. So since I have written S only, so in the ith column, ideally there would be S of I. Like this is column 2, right? Like this arrow is at column 2, the second column. So since my S of 2 was 0. So therefore, ideally this entire column should have a zeros, all zeros. But since I flipped the diagonal elements, so the ith element, the second element on the top, has been flipped. So it is 1. So I have all the zeros except for the middle one, which is 1. Right? So that means that my column is divided into 3 components. Right? So I can say that initially, like from 1 to I minus 1. like 1 to I minus 1, it will have S of I. Then ith will be S of I bar, where bar means negation. Like 1 bar is 0 and 0 bar is 1. Okay. So the ith one is Si bar, and then again I plus 1 to n is equal to S of I. So like in this column, the first one is 0, and again these ones are 0, and this one is 1. So as you can see that each column is divided into 3 components. Like the first column is divided into this component, then like this component which is empty, and this component. Then this column is divided into this component, and this component. So and so on. So that's what you can actually exploit. That in general case, initially we started with n square components, right? Like this is the general case. What would we do? We would do that initially all of these components are independent, right? They are independent. And then one by one, we would join the adjacent zeros. So I'll join this, I'll join this, I'll join this, I'll join this, and so on. So I'll join this also. So now some of the components are joined, but we started with all single components. So in this one, in the general case, there were n square components initially, and we joined them, and finally we figured out that we would need to find the highest size. But in this case we can see that there are only 3n components, not n square. Like for every column it has 3 components, like this one component, this another component, and this another component, this and this, like this component, this component, this component, and this component, and this component, right? So in our grid it has only 3n components, because each column has n components, sorry, 3 components. Each column has 3 components, so therefore there are at max 3n components. And now all we got to do is just connect those which have adjacent zeros, right? So of course in the same column we cannot have, like, of course in the same column we have already connected 2 adjacent zeros. So now the only way is that in 2 different columns, or basically in 2 adjacent columns, it might be happening that there are two zeros side by side. Like in this case, these 2 zeros are side by side, so we have to connect them. We have to join them using a DSU, right? So intra column we have already handled, and in inter column we have to handle that. Like we have to join them. So what we can just do is iterate over the columns, right? Like let's say I am at column I, for example. Like let's say I am at column I right now, and I want to join it with column I minus 1, right? So I will join it if there are 2 adjacent zeros. All right. So let us do some casework now. Like I am at column I, like S of I and S of I minus 1. It is possible that maybe S of I minus 1 is 0 and S of I is 0. So how will that look like? That will look like S of I minus 1 will have 0, 0, 0, 0, and there will be 1, and there is 0, 0. And S of I will have 0, 0, 0, 0, 0, and then it will have 1, and then 0. So these components are there in the first column, and these components are there in the second column, right? So what we can do is just connect which components. I can connect the bottom 2 components, and I can connect the top 2 components, right? That's what I can do. So if S of I equal to 1, so S of I minus 1 equal to 0 and S of I equal to 0, then I can connect the top 2 components and the bottom 2 components. Then let's say if S of I minus 1 is 0 and S of I is 1, then what I do? Then what I can do is, let's see. If S of I minus 1 is 0, then it will be 0, 0, 0, 1, 0, 0, let's say. And if S of I is 1, so it will be 1, 1, 1, 1, 0, 1. Right. So here what would we connect? Here we can see that these two zeros are adjacent. So we can actually connect the middle component. Like, again, we have three components, right? Three components we have. So we can connect the middle component of the ith to the bottom one of the I minus 1. Right. Now let's say we have 1 and 0. In that case, what we will do? Again, let's see. In that case, I will have 1, 1, 0, 1, 1, 0, 0, 0, 1, 0. So I will have to connect, like, wait, this top one of the ith to the I minus 1 ka middle one. And if I have 1 comma 1, if I have 1 1, then what will it happen? Then basically I have 1 1 0 1 1 and 1 1 1 0 1. So in this case there are no adjacent zeros, so I will not connect anything. So yeah, all of these three cases we'll explore and we'll connect the relevant sets, and we'll basically maintain the number of zeros in each component. Like, in this component the number of zeros is 1, in this component it is 0, in this component it is 1, it is 0, and in this one it is 3. And then we are joining, like when we are joining the components, we'll update the number of zeros by their sum. Like, since this has 3 zeros and this has 1 0, so I'll say that this new component now which I have joined, this now has 4 zeros. And yeah, that's what I'll do, and that's how I can solve the problem, because we have just 3n um, 3n components initially, and I can join them by just doing some case work, because the intra column ones are already joined. The inter We only need to join two adjacent columns. So I am looking at, can I join I minus 1 and I? Like, can I join the column I minus 1 with column I? So for that I have made 4 cases and I just analyzed every case. Alright. So that's the solution for this problem. That you can use DSU and do that. So is that clear, guys? I hope it is clear. If anyone is still watching, I hope it is clear. So since I'm not getting any doubts, I'll assume that it is clear and I'll just show you the code. Okay, so here is the code. I have this DSU struct which has find and unite. So yeah, I have int n cnn, string s cns, and I make a DSU of 3n size. Then I'll have int j equal to 1, j less than equal to n, j plus plus. So what I'm doing here is initializing the DSU. Like, if s of j minus 1 is equal to 0, like if it is 0, then what will it look like? It will look like, that column will look like 0 0 0, then a 1, then a 0 0 0. So in the first component I will have j minus 1 zeros, then I'll have no zeros in second component, and in third component I'll have n minus j zeros. Right. So DSU dot W of t. So W is just counting the number of zeros. Like I have another array in this which counts the number of zeros in that component. And while I'm joining, like while I'm uniting, in that only I'm just adding the number of zeros from B to A. Like when I'm joining this B into A, I am just adding the number of zeros of B into the number of zeros of A. Right. So I'm just doing DSU of WT, and T is here 3 into J minus 1. So essentially, like the first three are the like DSU of 0, DSU of 1, DSU of 2. This in this array, like, or in this DSU of 3n size, the first three components are for the first column, then the next three components are for second column, and so on. So I have, therefore I have 3 into J minus 1, and then I'm doing T plus 1 and T plus 2. And if S of J minus 1 is 1, then DSU of WT equal to 0, T plus 1 may 1, and T plus 2 may 0. Right. And then what we will do is like iterate over all the columns. Right. And then I have just casework that current and previous. If current is equal to 0 and previous equal to 0, then just unite T and TP, and unite T plus 2 and TP plus 2. So which is the topmost 2 and the bottommost, the top 2 and the bottom 2 of the both the columns. If current is 0 and previous is equal to 1, then unite the topmost of the current one and the middle one of the previous one. And if current equals to 1 and previous equal to 0, then unite the middle one of the current one and the bottom one of the previous one. Right. And finally the answer, we print the answer equals to 0. So I'll just iterate over all the components, and like if DSU dot find I equals to I, then that means that that is one of the components. Like if DSU dot find I is not equal to I, then doing DSU dot W of I does not make sense, because that is not in a component, that is not a component in itself. So if this is the case that I am on a component, so I'll do an ans equals to max of ans comma DSU dot WI, and then I'll see out ans. Okay. So yeah, this was the code, and yeah, I hope you like understood it. If you still have a doubt, then I'm here to clear that out. So if you have any doubts, then you can ask me right now. So again, I'll wait till 15 or 30 seconds. Yeah, because the problems were quite good. Like until C, it was pretty easy, but even this D problem was pretty good. And like C was lengthy, kind of. Not very lengthy, but and B was also not very straightforward. So that's why it took some time. Anyways, so yeah, I think you don't have any doubts. But like if you still have a doubt, then you can ask me in the comments. But yeah, so thanks for watching, and like all right, like thanks for watching, and I'll see you guys next time.